decimals. So if I write something like 0.6, that's slang. What's the correct way to read it?
6/10.
6/10, right? So 6 out of 10. And then it's a fraction when I say it properly, and then I can reduce it if necessary. This one happens to reduce down to 3/5 when I divide the 2 at the top and bottom.
Okay.
If I take something like slang 0.73, reading it properly, it's 73/100. Boom, it's a fraction. With a little bit of effort, we can see this one doesn't have to be reduced. So decimals to fractions, if we can name place values, conversion is straightforward. Fractions to decimals is a little bit more complicated. So that's what we need to take a look at next. So let's start with a really easy one. About the simplest fraction I can make is 1/2. And kids learn that one very, very, very young. Preschoolers got 1/2 down. Well, what's the fraction bar mean? It means divide. So I literally have to take 2 into 1. Now 2 doesn't go into 1, does it? Okay. However, I could say this is 1 0/100. And if I know where the decimal is in the dividend, and I have a whole number out front, we talked about this last class. In order to do long division, you have to have a whole number out front. If there's a whole number out front, then the dividend tells me where the decimal goes in the answer. So now I can pretty much ignore that there's a decimal point, and I can just proceed with regular long division. So let's see. 2 goes into 1 how many times?
0.
0 times. And I like to put the 0 there. 0 times 2 is kind of boring, so I'm going to skip that part. And then I'm going to say, okay, ignoring the decimal, 2 goes into 10. How many times? 5. 5 times 2 is 10. Subtract, and I get 0, and so I'm done. Right? 0 indicates the end of long division. And so I've just, with division, converted 1/2 into 5/10. Now, you guys have done this a ton of times before. I'm just kind of trying to bring you back to thinking about what it's like to be a kid. I tried to justify in class last time that you have to have a whole number out here for our division algorithm to work, because our division algorithm depends on counting. And what do we count by, usually? Don't we count 1, 2, 3, 4, and not those whole numbers? So our division algorithm kind of depends on that. You can trick your brain into doing it with fractions out front, but it's a lot harder to do. All right, so let's try another one. How about let's make it a little more challenging, 1/8. So that means 8 goes into 1. Now we already know that's pretty boring, so we rewrite it. 1 is the same as 1 0/10, isn't it? So then I just move along. Let's see. 8 goes into 1 0 times. I know the decimal has to go there, so I can start ignoring it. So then I say, okay, 8 goes into 10 how many times? Once. 1 times 8 is 8. Subtract, and I get a 2. That's not a 0 remainder, is it? So that means I got to keep going. To keep going, I just add another 0. Isn't 1 the same as 1 0/100? Yeah. So I'm still continuing the same problem. I have a 0 to bring down now. Let's see, 8 goes into 20 twice.
So
2 times 8, 16.
So what if it's like a ongoing number?
We'll skip that in a minute. So let's see. Subtract, and I get a 4. That's not a 0, so that means I need to put another 0 above. Bring it down. Now, I don't know about you, but I'm not always neat. And so sometimes I draw these lines when I bring something down to keep things lined up. If I have messy kids, I'll make them do it on graph paper. Depending how messy they are, like the graph paper I gave you today, those grids are kind of too fine. I might use like a centimeter by centimeter paper, or 1/4 inch by 1/4 inch paper to have my kids draw these on. 8 goes into 40.
5.
Oh, thank goodness. Why? because 5 times 8 is 40, and I get 0 remainder. And so finally I've come to a conclusion. 1/8 is the same as 125 thousandths, right? Tenths, hundreds, thousandths, 125 thousandths. So we could also use a calculator to play with this too, and we'll do that in just a minute. So let's try another one. How about 1/6? Let's try that out. So that means I want to take 6 into 1. And 6 doesn't go into 1, so I'm going to write it as 1.0. So what's the rule for division with decimals? The divisor has to be a whole number. Is my divisor a whole number?
Yes.
Yes. So that means I know where the decimal goes in the answer. The dividend tells me that. All right, so 6 goes into 1 0 times, 6 goes into 10 once. 1 times 6 is 6. Subtract, I get a 4. Okay, so I'm not done, am I? Put a 0 and bring it down. 6 goes into 40, how many times? 6. 6 times. 6 times 6 is
36.
6. Subtract, and I get a 4. Oh, wait a minute. Didn't I already see 4 as a remainder?
It'll go and repeat so you get 1.
Yeah. Once you see the same remainder again, you're stuck in a loop. And we'll do a couple of examples of that to find the loop. So what's going to happen next? Well, I got to put another 0 in. And I got to bring that 0 down. Ooh, this loop is right next to itself. So what am I going to get over and over again here?
41.
I'm going to get 44 for remainder, which was going to put a 6 in the quotient at the top. And so I'm going to get 6's over and over and over and over again. So we could say, there's a couple ways to write the answer. If I write an equal sign, I could say it's 0.16, and I can put a repeating bar over the 6 only. That says the 6 keeps repeating, not the 1. How about this? 0.166 with a bar over that. It's the second 6. What's that?
It's the same.
Same thing. Okay, how about this? 0.166 with a bar over both 6's.
Same thing.
Same thing, yeah. This one uses the least ink, so it's more popular. But when kids first get started with this, they're going to write all kinds of weird stuff. Some of which is right. Would this be okay? 0.16 with a bar over the 1/6.
No.
No.
Yeah, this is not the same. Not equal. Because that would be 0.161616 forever and ever like that. All right, let's do another one. This one's going to be a little harder. You're going to need some length on your paper. Let's try 1/7.
So how many times do you want us to, just the one time that you get the same remainder?
Once you, and I'll explain, we'll see why in just a minute with the next example. I think I can show why that's enough. So I'm going to take 7 into 1. And I said this is going to take a little while, so we might as well put a few zeros up there to start with. I'm going to put up 4 to start with and see if I need more. So now I just want to be careful. Okay, so let's see. 7 goes into 1, no times. I know where the decimal point goes. 7 goes into 10 once. 7, subtract 3, bring down that 0. 7 goes into 34 times. Is that right? 4 times 7 is 28. Subtract, I get a 2, and I'll bring down the next 0. And again, I'd like to draw those lines to keep me honest. If you're neat, don't worry about it. 2 times. 7 times 2 is 14. Subtract, and I get a 6. Bring down the next 0.
56.
8 times. Okay. 8 times 7 is 56. Have we seen a repeating remainder yet?
No.
Yeah, so just double check that. First, I got a 1, really, that's kind of a remainder of there. And then I got a 3, and then I got a 2, and then I got a 6. Well, what are the possible remainders anyway? With
Anything below
dividing
10.
by 7.
Anything below 7.
Anything below 7, yeah, so this is just a note. Possible remainders are 0, 1, 2, 3, 4, 5, or 6. If the remainder is 7, it means I didn't subtract enough out. That means I made a mistake. So these are the possible remainders. So there's only a limited number of remainders. So what's the most amount of times I can do this before I'm going to have to repeat?
7.
7, yeah, most I can go 7 times. Yeah. And if it repeats, you'll never see 0, because if you do see 0, you're done. It doesn't repeat. 0 is no remainder, right? End of problem. So it looks like I can at most go 6 times with 7 as the denominator before it starts to cycle. All right, so let's keep going. You guys are probably ahead of me by now. Subtract, that gives me what, 4. Haven't seen 4 yet. I have to add a new 0 and bring it down. Uh-oh, I'm running out of room. I wrote too big.
I know it ends in a second.
Okay. 5 is 35. Subtract, and I get a 5, 0, bring it down.
49.
7, 49, thank you. Subtract, and I get a 1, and now the argument is have I seen that one before or not? My claim is I have. It's right there. Because what's going to happen next is I'm going to bring down another 0, and there's the 10 I started right there. So what is the repeating pattern here? What would I put a bar over?
The whole thing.
The whole 1, 4, 2, 8, 5, 6. So whip out your calculator, hit 1 divided by 7, and see if that pattern pops up. So I'm going to ask my Google calculator. 1/7, and Google, come on, baby, there. I hit 1/7.2.
Mine only goes up to the 10th digit, and once it hits the second 1, 4, 2, 8, instead of 8, it says 9. It's rounded.
That's rounding up. Yeah, so mine is 14285.7, 14285. That's interesting. Mine
Yeah, yours goes to the
round.
11th.
Yeah. And there are calculators out there on the internet that will go as many places as you ever want to see. So one of my favorites is Wolfram Alpha. I'm going to ask Wolfram Alpha. See if a pattern emerges. I want to know about 1/7. Wolfram Alpha, throw you up. This guy right here. You see a pattern going on there? 14285.7, 14285.7, it's getting kind of boring. I could ask for more digits and hope, and more, and more, and more. Yeah, I think we got a pattern here. What about you guys?
So aren't there only a few numbers that don't have a limit to how far they'll go?
Yeah, so that's the question. So this goes on forever, and ever and ever. So here's the deal, though. So we made some observations that are going to help a lot in analyzing this. For any number, there's a set of possible remainders. Okay? If you happen to hit 0, you're done. If you don't ever hit 0, then it's going to go on forever. So my claim is that if you start with a fraction, one of two things happens. The decimal terminates. That means you hit a 0 remainder somewhere. Okay. The second option is it repeats. And the repeat means you never hit 0, but you always have a fixed set of remainders. Sometimes things take as long as possible. Like my example of 1/7. This has up to 6 different remainders. And it used all 6 of them before it repeated. Doesn't always work that way. So let's try another one. And we're going to do this on the calculator instead. If you could, on a calculator, type 1 divided by 11.
0, 9, 0, 0, 0.
Yeah, 0, 9, 0, 9. So 11 had the potential to have 10 remainders, but it turns out it didn't need them all. And it's just going to repeat that pattern forever. 0 and the 9 repeat. So check out 2 11s.
1 in 1 in 1 8.
Repeating forever. Okay. How about 3 11s?
Why is it basically multiply whatever number it is by 9?
That's an interesting. Why is this related to 9?
2, 7.
Yeah, 2 times 9 is 18. 1 times 9 is 9. Oh, that's 2 7. Sorry. 3 times 9 is 27. That's interesting. Yeah. Kelly? No, we don't have names for all the place values. They just keep going.
I have a question.
Yeah.
When we go back, there's a problem in the book that is related to this.
Okay, so let me do a couple more. Let's see, what do I want to try? Oh yeah, let's try, how about 1/9?
And it's just 1.
Yeah, a whole bunch of 1s, forever and ever. Okay, how about 2 9s? Okay, 0.22222, repeating forever. But just, I want to do something here first. Check this out. What happens when I add 1/9 to 2 9s? You get 3 9s, right? Okay. Now what happens if I add 1/10 to 2/10? What do I get? 3/10. What happens if I add 1 100th to 2 100ths? 3 100ths. 1 1,000th and 2 1,000ths. Do you see I can add infinitely long decimals together as long as I can see them, their pattern? So I'm pretty sure that this is going to be 0.33333.
It is.
Does that make kind of sense? 1/9 is 1's repeating, 2 9s is 2 repeating, 3 9s is 3's repeating. It's kind of cute. What would 7 9s be?
7 9 would be 7 7 7
7's repeating? Okay. All right. So I got another cute one. Check this out. Calculators, please. What is 23 out of 99?
2 3 2 3 2 3.
That's cute. 0.2323 repeating. Okay. How about 127 out of 999? That's cute. Kelly, what's up?
So anything to do with 9 always has a self in it?
Yeah, so without a calculator, I want you to find the following decimal. What would happen if I took 1,234 and divided by 9,999? What would I get as a decimal? I would get 1, 2, 3, 4 repeating. Got 1, 2, 3, 4, 1, 2, 3, 4. And that 1, 2, 3, 4 keeps going over and over and over again. That's interesting.
My phone does something a little interesting that every time I put in the next number, it'll show the answer that will come up. So I just go 1 9 will be this answer, the second 9 will be this answer, and there's a whole bunch of repeating equations that happen when you divide by 9, 99, 999.
Okay. Yeah, there's a lot. You can play with this stuff forever. So I want to back up just a little bit to this screen right here. Okay, so we have a pattern with 9s, right? We said that 7 9ths is likely to be 0.7777, and so on. So according to this pattern, what should 9 9ths be?
1 should be 1.
According to the decimal pattern, what should 9 9ths be?
0.999.
It should be 0.99999 forever and ever,
Which rounds.
which always rounds to 1. That's pretty weird. Crap. All right, so we're going to take this and we're going to twist it in a slightly different way. So I'm going to show you another one and see if you can predict the answer. What if I take 17 over 99? What's that going to be? 0.17, yeah, 17 is repeating. Okay. How about if I took
214 over 9.
7 over 90? I think that's going to be. Anyone guess? Let's get a guess wrong.
0.09, or 0.077777.
No, 0.07, 0.00.
0707. Okay, so we have a couple options: 0707 or 0777, like that. So just to double check, I think that top one right there would be 7 over 99, because I could write that as 07 over 99. So let's just double check. Type 7 over 90. What do you get?
7777.
07777. And if I do 7 over 99, that should be 0707070707. Okay, yeah. So this one actually goes down here. So what happened here? So does this one make sense, the 7 over 99 compared to other pattern? So that one's a little weird, so I want to just break that out a sec. So 7 over 90. Well, I kind of in there have a 7 over 9, which I know is a bunch of 7s repeated, right?
Mm-hmm.
But then it got multiplied by 1/10. Check that out. Does that make sense? 7 over 90 is the same as 7 nines times 1/10. I know that 7 nines is 0.777, blah, blah, blah. What happens when we multiply something by 10, 1/10, or divide by 10? Doesn't dividing by 10 just move the decimal point to make the number slightly smaller? So there's where we get that pattern 0.077, and just the 7 repeats. All right, so now we're going to do this backwards. So here's where it gets interesting. What I want to try to do is take a decimal and turn it into a fraction. Is that hard or easy?
Depends on the equation.
Depends, yeah. So if I just give you something like 0.25, is that hard to turn into a fraction?
No.
No, it's 2500ths, right? And then we can reduce. Eventually we'll get to 1/4. All right, so here's where the fun comes in. What if I give you something like 0.15 repeating?
That one is not a, it's either a 9 or it's a 7 or so on.
I think according to the patterns we just saw, that's probably going to be 15 over 99. Check it out on your calculator. What's 15 over 99?
15 over 99 is 1515.
1515. Now this reduces a little bit, right? 3 goes into top and bottom. So 3 goes into 15, what, 5 times? 3 goes into 99 33 times. And I'm pretty sure I can't reduce it anymore. So 5/33 is the same as 0.15151515. So I'm going to put another twist in it. What if I did 0.05 and just the 5 repeats? So that would be 0.0555. Okay, so what do the 5s repeating tell me? That's part of the answer. What does this part tell me?
It's over.
It's 5. Oh, almost, yeah. So this part right here tells me basically I have 5 ninths. And that part right there tells me I have a 1/10 in there. So it's 1/10 times 5 ninths, which should be 5/90ths. Double check what's 5/90ths on the calculator.
Uh, 1/10 and 5's repeating.
Yeah. And we could reduce this a little bit. What would it be, 1/18, I think? But it's that pattern up there. I'm going to make it harder still. In this one, we're going to use a trick to solve. Actually, I'm going to make it easy, then hard. Let's take the number 0.666666. We already know what the answer is, don't we?
Yeah.
What is it?
6 over 9.
6 over 9 or 2 over 3? Okay. Let's make believe we don't know the fractional answer. So we're just going to call it x for a minute. Now, this goes on forever. Would you agree going on forever is kind of a problem? Because I can't go on forever. Okay? So that's weird. So infinity is weird. I want to get rid of the forever part. So here's what I'm going to do. I'm going to multiply x by 10. What happens to the other side of the equation when I multiply by 10?
You multiply that side by 10.
Yeah, and how does that simplify?
It gets moved over the decimal.
Yeah, shift the decimal, so that's going to be 6.666666, and so on. Okay. Oh, wait a minute. Both of these numbers have the same decimal part. 6 is repeating forever. Wouldn't it be nice to subtract off that repeating part? So here's what I'm going to try. From the 10x, I'm going to subtract x. X, remember, is 0.66666, repeating forever and ever. And when I subtract on the right side, what goes away? That crazy infinite part. What's left on the right? Just 6, that's awesome. On the other side, what happens if I take 10 x's and remove 1x? I get 9 x's. And so what's left over that has to be the answer? 6/9 divided by 9, right? Which is also 2/3. So there's a little algebraic trick to determine that 6 is repeating has to be 2/3 or 6/9.
And so that
Without a calculator. So I'm going to question. What was that, Christian?
I don't even remember what I was going to say.
Okay.
That's just really
Isn't that crazy? So the trick is if I can fiddle with the number and make the infinite parts match up for two numbers, I can do a subtraction and make the infinite parts vanish. So I'm going to try it on a slightly harder one. So you're going to have to, I'll go slow and just ask questions if you get stuck. So I'm going to take 0.16666. So it's just the 6 that repeats, the 1 stays still. And I'm going to say I don't know what that fraction that is, so I'm going to call it x for it. So I want to create a fraction that has basically the same infinite tail, because the infinite tail is trouble. Well, what was the trick earlier? What did I do? I multiplied by 10. Okay, so let's try it here. So I take 10 times x. So that means on this side I get 1.66666. Okay, so does the infinite part really disappear? Yes and no. Well, they don't exactly match up here, but they do match up that way forever. Agreed? Yeah, so I can pull this off right here. Right, so what I'm going to do is underneath I'm going to write minus x, which is minus 0.16666. And so what I know is that since there's always a 6 out to the right there, all of these guys, when I subtract, are going to be zeros. Except when I get to here. What's 6/10 minus 1/10? 5/10. 1/10. 1 whole minus no holes. One minus nothing is 1/10. And then on this side, what do I get? I get 10 minus 1 is what, 9x? 0.5 zeros forever. Is the zeros forever a problem? Heck no, not a problem. Dividing by 9, I get 1.5 over 9. I do have a slight problem. Is this a fraction? No, it's a division problem, but it's not a fraction. A fraction needs to have a whole number top and bottom. But I can fix that. What could I multiply top and bottom by to fix that? 10, yeah, multiply by 10. So that means I have 15/90ths.
multiply both by,
And then, what's that?
multiply both by 15, right?
No, multiply by 10 to get this.
And then
Times 10 times 10. And then I want to try and reduce this. And the question is, does 15 go into 90, or do I have to do it easier? I can't do that in my head, but I do know 5 goes into top and bottom, or maybe 3. I'll do 3 first. 3 goes into 15 5 times. Let's see, 3 goes into 9 3 times, so 5/30ths. Oh, now I can do it. 5 goes into 30. This is 1/6. Oh wait, we saw that before. Remember we did 1/6 earlier with the other direction? We did the long division. So here's the point, and I did this in 2 directions. When we were doing fractions to decimals, I argue that there's always a limited number of remainders. So either you have to repeat or you have to terminate. There's no other option. Here I went the other way. I took a repeating pattern. I got rid of the infinite repeating part, which means I can always turn a repeating pattern into a fraction. So I can take it both directions. So what's the moral of this story? The moral of the story is I've just confirmed that every single fraction, right? What's another name for fractions? Anybody remember way back in chapter 6? 2 words. Initials are RN. No, not real. Rational numbers, yeah. Fractions are also known as rational numbers. Rational numbers. Every single fraction or rational number that exists either terminates as a decimal or repeats a pattern. Repeats a fixed pattern. By fixed pattern, I mean I could go down to a shop that makes rubber stamps, and I could make a rubber stamp of the repeating part, and I could go stamping it down the road all day long, forever and ever. Yeah. So here's the next question. Well, are there decimals that don't terminate or repeat?
That's pi.
Pi is one of them. So we have seen, so there exist decimal fractions that do not terminate nor repeat. Oops. Repeats. The most popular example of such a number is pi. Wait a minute. If they don't terminate and they don't repeat, they can never be written as a fraction. That's the consequence. There are some numbers that don't exist as fractions.
Is that why it has its own symbol?
Yes, that's one reason it has its own symbol. Yeah. There's another one you've seen before. I'm going to show you.
Isn't it E?
Oh, I wasn't thinking of E, but that's a good one. I'll write that down in a second. I'm trying to draw something here. What kind of triangle is that? A right triangle. If I put a 1 there and a 1 there, what kind of triangle is it now?
Isosceles.
Equilateral. No shit. Isosceles. Debbie's right. I'm wrong. Thank you, Debbie, for saying good math. Yeah, it's an isosceles right triangle. What famous thing do you know about right triangles? Anyone?
That if you match one, flip it over, it matches the other side.
No, that's not what I'm thinking of. Kelly?
Pythagorean.
Pythagorean theorem. Anybody remember the Pythagorean theorem? A long time ago, yeah. Pythagorean. Can I spell it? Yeah, there it is. Theorem. Pythagorean theorem says if you take each leg and square them, okay, so that would be 1 squared plus 1 squared, and then you add them up, that's always going to be equal to the square of the long side. Here's the long side over there. Long side's always opposite the right angle. So that's always going to be equal to long squared. Okay, well, let's see. What's 1 squared? 1. What's 1 plus 1? Okay. So this says that the long side squared has to be equal to 2. What number can I square to get, what number can I multiply itself to get 2?
2.
If you think way back to your algebra class, you learned how to use the square root symbol to cancel a square. Remember that once upon a time? So it turns out the long side, in this case, has to be the square root of 2. Okay. This is both cool and trouble. The Pythagoreans were a math/religious cult a couple thousand years ago, and they believed that the world was rational. What do they mean by rational? They mean you could describe it with math and rational numbers. one of the Pythagoreans showed that this number couldn't possibly be a rational number. Do you know what they did to him?
Killed them.
They killed him. Yes, very brutally. Yes, they very brutally killed him. That was a problem. The famous Pythagorean theorem showed the world is not rational. It can't be described using rational numbers. We need more numbers. These kinds of numbers that can't be written as a fraction are called irrational. We'll deal with those in chapter 8. We have one more section in chapter 7 to do on percents and interest rates.
And we're done already.
What's that?
Then we're done already.
Chapter 7? We have one more day for chapter 7.
So we'll have a test next week.
No, we're going to do chapter 8. Because it's really, it's more on decimals. Yeah. So,
I hate interest rates.
so what we're going to do before we have a test is do all of 7. So we have percents and interest rates to do. In chapter 8 is a lot of algebra, and I'm thinking about not doing algebra unless anybody really wants to. Adrian's thinking about it.
No,
so
I
maybe.
just have failed algebra so many times and redone algebra so many times, I feel like I'm
That I need to do it.
No.
Maybe I'll just do an abbreviated version. They have like 4 sections in algebra. Maybe just do an abbreviated version of it. I don't want to spend too much time in algebra because I really, really, really want to do probability. There's a lot
That's
of-
even worse. Let's do
Okay,
it.
algebra, all of
No,
this
there's a
algebra.
lot of fun stuff in probability. We get to throw
Probability
hoops
and
and baskets and roll dice,
Are the devil. Sure.
play with cards. Okay, so you guys, so this is section 7.3 here. So start working on that homework. As far as activity goes, we're up through activity 9, I think. But we're not quite ready for activity 10. And then I apologize, I am still not done grading your exams. And so I am 3/4 of the way through.
Do you have part of mine done?
I finished everybody's in class, I have not finished the take home. I can give you your in class for now, yes. And the exams did not go well, so we have some review to do. And so we're gonna have to schedule some review sessions. If anyone did not get a grade they like. And you certainly got grades I didn't like, so review sessions are mandatory for some of you. Because I need you to correct anything that wasn't right, if we do need help. So we're gonna schedule those. So for those of you who didn't get the test Monday, I'll give it to you this Monday. And that's it for today. You're right on the edge of needing review, so I would say you should get a review time with me. Because you gotta make that up before the final. So we should schedule it. So I'm free before this class every day, and I'm usually free after this class, and I'm free other times during the week. So we'll talk about scheduling something. Most of you have something right after this, don't you?
Yeah, well, not that
No, we
You just need to go.
that you do.
yeah.
Okay, look at that.
I didn't think.
What days and times is that?
Monday and Wednesday.
For the people that have mandatory studying,
Yeah,
how would that work with me?
we'll do just a you and me Google chat.
Okay.
Yeah, so we'll schedule that. And let's see, I emailed you your in class, right?
Yeah, and I misread the instructions when it said to do the diagram. I thought it meant to let the diagram explain it. So,
Okay, so you can give me a good explanation for that one?
yeah.
Okay. So let's see. Yeah, give me 1 minute, Debbie, and I'll talk about it.
Well, they're doing the pop-up Rex gallery from February and I know they're getting nervous. March showing the gallery starting.
Probably not, like I said, next week. Yes, probably not next week,
And
so.
they're doing it.
You don't have, you've got the all-day thing going on? Do you have any time this week? Are you on campus at all this week?
No, because my daughter is has a my daughter's trying to go to George Fox University and she's got a scholarship deal, so we're leaving tomorrow.
You're leaving tomorrow. I was gonna say, can we do a video chat this week?
No,
Yeah, do a video chat next week, maybe like after you get out of school?
we could maybe do it next week, a video chat.
On the days when I don't have this class, so you're in school all day next week?
Testing some out.
We work as a teacher basically all
Okay.
next week.
So I have class till either 4 or 5 each day.
Okay.
So we could do a chat on or Tuesday or Thursday if that works.
Yeah, they have the assignment.
Um,
Or we could wait till the week after and do it for that. I
I'd
don't wanna
rather do
wait
it,
too long.
I'd rather do it in person
Okay.
just because for me it's easier and then I'm here Monday and I get done usually with my test program. Usually the longest thing is about 2:30, sometimes it's
The
sooner
Monday
than that.
after next,
Yeah, a week
Okay.
from Monday.
we have class at 3, so that would give us at least a little time before class.
Yeah.
And then we can move some time.
Right.
Let's plan on that for now.
Or I could just tell them I have to leave them too and leave them too.
So I have numbers. Like there's the answers.
Oh, yeah.
Like there's 2 points.
Okay.
Sorry, Drew, just didn't help.
Okay. So let's see, so. Okay, so we're gonna meet probably.
There was the first one. This is basically all of it. Oh, no, I showed that on the paper.
So Monday before this class?
So,
So hopefully next week,
ratio things.
see you or just come for like, you're not
Whatever
Tomorrow?
saying is
Yeah,
that
I'm
time they are.
we some
That's 39.
Oh,
Oh,
okay.
okay.
I had class at 12 to 4. So just before 4.
Thank you.
Okay, so Monday right before each class.
But I just turned it.
Tomorrow morning.
This is part of the morning, so time to get
I have
later.
and we're until 11.
Okay, so 9, 10? 10 o'clock, okay, so 10 a.m. Thursday. Thursday, okay, and then, let's see, Debbie, you're still out there.
Do you want this or do you want this?
So you did pretty good, Debbie, you don't have to have mandatory review, yours is optional. So do you want to schedule a time to do a video chat, or do you want to try doing corrections and then see how it goes?
I think I could just try doing corrections. Like I said, I think I know how to explain it. I just, when I read the instructions, I thought the picture was supposed to explain it.
Okay, no, yeah, usually when I want explanations, I want words.
Okay.
And then, I know you emailed me your take-home part, and I cannot find it in my inbox. Can you resend that to me?
Yes.
Okay, thank you.
Do you want this or do you want this?
You keep that, okay. Yes, because you need to start thinking about corrections on that.
Yeah.
So are we correct? Greg, you are an optional reviewee. You have to correct anything you didn't get right. You can meet with me to go over it or not.
Well,
Would you be ready to do the take home?
I have not finished it.
Okay.
I want to keep reading this tonight, tomorrow. I can scan an email. You could go either way. If your take-home exam percentage is lower than the in-class percentage, it will affect your grade.
Are we correcting the taking?
No.
We're correcting the one in class.
So correct in in-class.
Well, I'll
Have the
let-
in-class back.
I'll let you know, once you get it back, I'll let you know.
I didn't give you your in-class back yet? Yeah, I did.
Oh, you did?
Or Monday, yeah, I gave it to you Monday.
Oh, I thought it was the take home.
No, it's
My bad.
in-class.
Okay.
Yeah, yeah, so start looking at that. And then I did post my answers in the doc sharing section to the in-class. So start trying to correct them, take a look at my answers, and then see.
I think I lost a couple points on this by not putting what's correction was.
Yeah,
I was like 4 points off.
so your explanations.
Yeah.
Okay. And the corrections are part of your grade, so you gotta do corrections. Corrections are mandatory, meeting minutes. Say that right?
Well, let me re-
Corrections are mandatory. Meeting with me can't be optional.
let me review it this week and then
Okay.
if I have any questions.
Sounds good.
Please, when you talk about, correct it all the way.